Today we're on section 5.2 and we're dealing with logarithmic functions. We want to let a be any positive number as long as a is not equal to 1. The logarithmic function with a base of a, which we write log and then a subscript a, is defined by log base a of x equals y being equivalent to a to the y power equals x. Now the thing we have to understand about logarithms is they're really asking a question. When you see this, the question it's asking is a to what power equals x? And the answer to that question is y. And so when you look over here, that's what you can see. A to what power equals x? It's to the y power. And so that's the idea of a logarithm. Now, this equivalence right here is something very important that you're going to need to know. We're going to be transferring back and forth in between these two forms. This first form is what we call logarithmic form, and the second one is what we call exponential form. And we will be practicing going back and forth between those two forms, and it's very important that you can do that. So again, the description here, log base a of x is asking for the exponent to which the base a must be raised to get an answer of x. So the first thing we want to try is to rewrite these things in exponential form. Now the way I try and summarize, again, this very important rule up here, is notice that the base in each of these is a. One is the base of the logarithm, one is the base of the exponent. So the base does not change. The other two values, though, notice in the first one, x is by the a and y is by itself. But in the second one, y is by the a and x is by itself. So the other two kind of switch spots. So the first thing we always identify here, like in problem A here, is we want to identify the base. And the base is this number right here, it's 10. So then notice the 100,000 is by the 10 originally and the 5 is by itself. So when we rewrite it, the 5 goes with the 10 and the 100,000 goes by itself. So that's how you rewrite that in exponential form. For B, same idea. You identify the base first, 5, and notice that the s is by the 5 originally and the r is by itself. So when we rewrite it, the r is by the 5 and the s will be by itself. So that's how we rewrite things from logarithmic form to exponential form. So now in example 2, we're going to rewrite these from exponential form back into logarithmic form. But the process is the same. We identify the base. This one has a base of 2, so we're going to start out log base 2. Notice the 3 is by the base initially and the 8 is by itself, so now the 8 will be by the base and the 3 will be by itself. So log base 2 of 8 equals 3. Same process here, identify the base, which is 3, so it'll be log base 3 of 1 over 27 equals negative 3. So rewriting them doesn't require any math, it's just you have to know how to put them from one form to the other. And that leads us into example 3. We want to evaluate these logarithms. So the first one, log base 10 of 1,000, I'm just going to write equals x here because that's going to help us. Now we can rewrite this thing as 10 to the x power equals 1,000. And so hopefully we know that 1,000 is 10 to the third power. So the only way that this statement is true is if x equals 3. And that's our answer. So again, the goal is to find the exponent that we have to raise the base to get, in this case, 1,000. So again, for this one, we've got log base 2 of 32. So that is going to give us 2 to the x power equals 32. And continuing along that line of thought, 2 to the x power equals 32 is a power of 2. 2, 4, 2 cubed is 8, 2 to the 4th power is 16. 2 to the 5th power is 32. So that tells us that our answer is x equals 5. So that the simplification or the evaluation of log base 2 of 32 is 5. Now for part C, this one's a little bit different because when we rewrite it, we get 16 to the x power equals 4. Well, we don't have a really good way of figuring that out, at least not right off the top of our head. So what we have to do is a little trick, not really a trick, but a mathematical procedure where we want to write each of these with the same base. And if you notice, 16 is 4 squared. So that's 16 to the x power is 4 squared to the x power. And 4 is just 4 to the first power. Now some of you may have seen that they're both powers of 2 also, and that's fine. You can use 2 and you will get the same answer as long as you do it correctly. But we want to remember the rule for power of a power is that we multiply these. So this is going to become 4 to the 2x power equals 4 to the first power. And the same as we did before, the only way that's true is if 2x equals 1. And then our last step is divide by 2. So we find out that in this problem, x equals 1/2. Now we want to go through some properties of logarithms. And these properties are really based on the definition. So the first one is log base a. So any base, log base a of 1 is always 0. And the reason is, again, back to our definition, that a to the 0 power equals 1 for any a value. So that's how we get that particular property. The next one, log base a of a equals 1. Well, again, if we rewrite that, the reason that works is because a to the first power equals a. And so that will work as long as the base of the log is the same as the number you're taking the log of. The third property, and this one, again, it starts getting a little confusing because it's so obvious, but the question they're asking here is a to what power equals a to the x power? And do we see that it's a to the x power equals a to the x power? The simple way of doing this is as long as the base of the logarithm is the same as the base of the exponent, they kind of just cancel each other out and you end up with whatever the exponent is. This one is a similar process, similar property, and again you can see that the base of the exponent this time and the base of the log are again the same value. So what happens is when they are the same, they're just going to cancel out and you get whatever that exponent is. So in example 4, we want to evaluate log base 5 of 5. Well, using that, I think it was the second property, we know that that answer is 1 because 5 to the first power equals 5. For B, log base 3 of 1, using the first property, we know that that is 0 because 3 to the 0 power will equal 1. For part C, this was the last property that we looked at, and we can see the base is 6 for the exponent, the base is 6 for the logarithm. That answer is just going to be 3. And then for D, log base 7 of 7 to the 15th power, those bases again are both 7, so our answer is that that's going to be 15. So what we want to do here is we want to graph f of x equals log base 2 of x by graphing y equals 2 to the x power. If you remember, we graphed this exponential the other day, and I'll just verbally put in some points. If you think about 2 to the 0 power, we know that's 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power, if it fit, would be up here around 8. It's off our graph. Here, I'll put it in white so you can see it a little better. Then 2 to the negative first power would be 1/2. 2 to the negative second would be 1/4. And remember what happens with these, they just keep getting closer and closer to the x-axis. So as we look at this, That is our exponential function. Now, the key thing with logarithmics in relationship to exponential is that they are inverses of each other. And so, what happens is, with inverses, we switch the x and the y values around. So this point is 0, 1. So this point will be 1, 0 for the logarithm. This point is 1, 2. So this point will be 2, 1. 2, 4 becomes 4, 2. 3, 8 becomes 8, 3. And then these values go back this direction as well. And so we can see what happens with this one is we get, whoops, missed that one. We get that curve going off to the right. Now in the exponential, you remember we had a horizontal asymptote of y equals 0. With logarithmics, we have a vertical asymptote of x equals 0 because, again, they're just switching x and y values. We also have the intercept here is 0, 1. Well, on the logarithmic, the intercept is 1, 0, again, because the x and y values are switching around. And if you remember when we talked about inverses before, we realized that inverses are always going to be a reflection over the y equals x line. And so you can see it's a reflection over that diagonal line. Here's a little bit nicer picture of it. And you can see that the red one is the exponential, the blue one is the logarithmic. So now we want to graph f of x equals negative log base 2 of x. So if you remember, log base 2 of x looked like this. I'll try and quickly sketch it. So this is the original. What's going to happen when we put a negative in front of it? It gets reflected. So all these points are reflected over the x-axis. So our graph is now going to look like that. Okay? And again, you can see that a little bit nicer here. The red one is the original, the blue is the reflection. Then for the other one, we've still got our original here. And in this one, what happens is we are reflecting over the y-axis. So this point is going to move over here. This point here will move here. And all those points are reflected in this direction. So what we get is that shape right there. Here's a little bit nicer picture of it again. Red one is the original, and the blue one is the reflection. So for this one, we want to find the domain. F of x equals 2 plus log base 2 of x. In this case, our domain for the others, if you think about it, was always the positive values, okay, unless it was reflected or something like that. The domain in this case, what has happened to this graph? It has moved up 2 units. So the original one was right here. My graph is getting worse and worse the more times I draw it. But everything moves up 2 units. This moves here, this would move here, this one here, and this one there. So everything moves up 2 units. And notice, still our domain is that x has to be greater than 0, or we could write it in interval notation from 0 to infinity. So 2 different ways that we could write it, x such that x is greater than 0, or from 0 to infinity. So looking at this one, find the domain. Think about, again, the transformation here. This one is moving to the left 3 units. So instead of the asymptote being right here at 0, it's back here at -3. And everything is shifted to the left 3 spaces. So this is going to be here. This will be here and here. And again, our graph is going to come through and look like this. And so what is the domain? The domain is, in this case, that x has to be greater than -3. So from negative 3 to infinity, and we can sketch that function there. So another logarithm a special logarithm that we have to deal with is one that has a base of 10. This is called the common logarithm, and so you'll actually never see, well, I guess I shouldn't say never. Very seldom will you ever see log base 10 written out, because this is the abbreviation that means log base 10. So anytime you just see log and then a number, it means automatically log base 10. As we look at example 9, we're going to use a calculator to evaluate this. And if you'll notice on your calculators right over here next to the 7 is the log button. So if we want to find the log of 132.6, we just type in log and then 132.6, close our parentheses and hit enter, and we get our answer, if we round it off, 2.1225. Then for the second one, log of 5, we do the same thing. Just log 5, close our parentheses, hit enter. We get 0.6990 if we round that off to 4 decimal. So for example 10, the perception of loudness B in decibels of a sound with physical intensity I is given by this function, where I sub 0 is the physical intensity of a barely audible sound. Find the decibel level of a sound whose physical intensity I is 100 times that of I sub 0. So when we do this problem, we've got, for our particular situation, 10 log, we've got I sub 0 on the bottom, and since I is 100 times that I sub 0, we can just put in 100 I sub 0. And notice what happens. These I sub 0s cancel out. So now we have 10 log of 100. And remember, this means log base 10. So the question, again, that this is asking is 10 to what power equals 100? And hopefully we know that that is 2. So our answer to this question is the decibel level of a sound whose intensity is 100 times greater than I sub 0 is 20. Another special type of logarithm that we need to deal with has a base of e. It also has an abbreviation. This is called the natural logarithm, and we write that as ln. So again, just like with log of x, when you see natural log of x, that is the abbreviation for having a base of e. So you won't see very often log base e of x written out. You won't see log base e, you'll just see ln. Fortunately, the properties are identical for these. Natural log of 1 equals 0 because e to the 0 power equals 1. Natural log of e equals 1 because e to the first power equals e. Natural log of e to the x. Again, the question they're asking is e to what power equals e to the x? And the answer to that is x. But again, anytime those bases are the same, they just cancel out. And e to the natural log of x equals x, same reason as we had for property 4 on the other logarithms. The other logarithms covered actually any base. They're just pointing out specifically that still works with the base of e. So then, evaluating a natural log of e to the 5th power. Remember, the question that's asking is e to what power is e to the 5th? And that is that third property. It's just going to be 5. Now b is a little bit trickier because we have to rewrite this. 1 over e to the 3rd is e to the negative 3rd. So when we get that answer, we get negative 3. For example 11 part C, we want to take the natural log of 5. So if you'll notice right underneath the log button or right next to the 4, we have the ln button, which remember is log base e, and we call that the natural log. So we're just going to type in ln and then the 5, close our parentheses, and hit enter, and notice we get 1.609. Now for number 12, we want to find the domain of this function, and here's how we do this. We know the stuff in here has to be positive. We've discussed that the domain is positive numbers. So here's what we do. We have to find out what the boundaries are. In other words, when does this thing equal 0? And if we do the math, we get 4 equals x squared. So x will equal, when we take the square root of both sides, plus or minus 2. So we've got some boundaries to consider. We've got from negative infinity to negative 2. We've got from negative 2 to 2. And we've got from 2 to infinity. Since 2 and negative 2 are the boundaries, we divide up our numbers into 3 sections using those 2 boundaries. So then we just check which ones give this value or make it positive. So let's try out, let's say we use negative 5 as a test value. So 4 minus negative 5 squared, well, we can see that is a negative number. So that one can't work. If we try out, let's just say 0. 4 minus 0 squared, that's a positive. So that one works. And then for the other one, let's just try 3. 4 minus 3 squared, that is a negative, so that doesn't work. So our domain is this middle section from negative 2 to positive 2. Problems that you should take a look at here on section 5.2 are listed there. You'll have time to work on that in class tomorrow, but go ahead and try and get started on some of those tonight so that you can ask some questions tomorrow in class.